Hello, so today we are going to do problems from weekly contest 125. The second problem is minimum operations to exceed threshold value. Number 2, the first one is sort of slightly similar, but a little bit easier, of course. So this one, we have an array of numbers and we have an integer k. And we can do one operation where the operation you take the two of the smallest integers in your array, let's call them x and y, and you remove them, okay? And then you take the min multiplied by 2 and then add up the max of the 2 and you add that back. So you take out the 2, you do this equation here, and then you add the result back. So you can think of it, the array size reduces by 1 each time. And you can apply this operation, of course, only if the size of the array has at least 2 elements, because otherwise you can't really remove. And the goal is to return the minimum number of operations that you need so that all of the elements remaining in the array are bigger or equal to k. Okay, so looking at the constraint here, the array size can be pretty big, so we can't really do an open squared solution. But if you think about this a little bit here, what we are required to do is just remove the smallest element, the 2 smallest elements, and then add back this. And we want to return the minimum number of operations. And of course, the minimum number is just going to be the number of operations in this case, because you take the smallest 2 each time. So we already do a greedy approach within the operation itself. And so as soon as the smallest element is bigger than k or equal to k, we are done, right? So when you have any problem that asks you to remove the smallest each time, you should always think about using a priority queue, or what's called a heap queue in Python, okay? And so with a heap queue, the other important thing, let's say we convert this array, let's call it A, to a heap queue. So we heapify it to have it be a heap. Then to get the minimum of x, to take the 2 smallest element, we just need to pop from the heap queue, because if you do pop like this, that will return you the first smallest element. If you do it again, that will return you the second smallest element. And then you can also check if the condition is that we want to know the number of operations it takes until the array, all the elements in the array are bigger or equal to k. And for all the elements in the array to be, for all a in A to be bigger or equal to k, all we need to check is that the smallest element, which is in the case of a priority queue, is the element at position 0. If that's bigger or equal to k, then we know the remaining element are also bigger or equal to k, because the smallest one is bigger. So what this tells you is we can actually do something in the order of Venn or Venn solution just using a priority queue, right? And so we can just do something like this. While the smallest element is smaller than k, we should keep going, keep doing operations, and we need to keep track of the number of operations we do. So let's just actually bring this back up here, move this. So each time we do this, we should increase the number of operations, but also we need to add the elements that we get from the min and the max. Now, one thing to remember here, this is the first smallest element that we remove. So this is actually the minimum between the two, because it's the smallest. This one is smaller than this one, so it's the minimum. And this one is bigger than this one, because by definition of a min priority queue is that min heap is that the first element we remove is the smallest of all of them. And then this one is the smallest of the remaining. So this one is the second smallest. So we can this one we know is the max between the two. So this is what we want to add back. And so if we just use the min values here, and we can use the max value here. And this is what we want to add back to our queue. So let's just do a heap queue, heap push, and we add this. And then at the end, we can just return our operations. Okay, so it looks good. Let's submit. And that passes, okay? Now, these operations, if you just do heap queue Python complexity. So it's O of log n for push and pop. Okay, so these two are O of log n. And so overall the core here is O of log n. And each time we reduce the size of the array by 1. And so this is O of n. So you have O of n log n solution. We should pass with the constraint we have. Yeah, so that's pretty much it for this problem. Thanks for watching and see you in the next one. Bye.